But it's my pleasure to introduce Michelle Vrettos, who is our guest speaker this evening. She's assured me that her presentation is very short, but many of you will already know the name of Michelle. Many of you will have read an article that's appeared in the September-October 2021 issue of African Bird Life. It was entitled Racing Stripes, and it was about her research with Arjun Amar on the dark malar stripes of peregrine falcons. She's a member of the Cape Bird Club too, and you will also have read about her in the November 2021 Promerops, where Johan, in the Bird's Eye View column, which is put together by the committee, welcomed her in her role of running the education program at 2 primary schools in the Steenberg area. We're so lucky to have this young lady on board. She's got a good rapport with kids, and her love of birds and birding can only rub off on them and inspire them immensely. She's going to be sharing with us something of her peregrine falcon research. Over to you, Michelle. I'm going to stop screen sharing, although it says that it has stopped from my side, and you can take over and share your screen, Michelle.
Okay, good evening, everyone, and thank you to Priscilla for introducing me. So as Priscilla said, my name is Michelle Vrettos, and I'm a master's student at the Fitzpatrick Institute of African Ornithology at UCT. And I did my honors at UCT in 2019, and I was looking at the relationship between solar radiation and the dark malar or facial stripes of peregrine falcons. And my master's research is just an extension of this project to the rest of the falcon species. So last year, I also managed to get a journal publication out of my honors research that also generated quite a bit of media buzz and was reported on quite widely in the popular media outlets, although they were not always the most scientific outlets. As you can see, I was particularly amused by this article in the bottom right, using a photo of a bird that is quite clearly not a falcon. So some background on my research. So when we talk about falcons, we are usually talking specifically about diurnal raptors in the genus Falco, which are part of the falcon family, Falconidae. And there are approximately 38 or 39 species, depending on which taxonomic authority you ask. So something that is particularly interesting about falcons is that they're not actually closely related to other raptors. So their closest relatives are actually parrots and songbirds. And they're therefore an example of convergent evolution with the so-called true raptors, the Accipitridae, which are the hawks and eagles. Since they're not closely related, but they've independently converged on a similar body plan due to their similar ecology and lifestyle. So compared to other raptors, falcons are typically quite small. Many of them are highly agile, and they often have these distinctive pointed wings. And many species also specialize in hunting birds. So we actually have quite a high diversity of falcon species in Southern Africa. We have 15 species that occur here, although 6 of those are wintering migrants, like this photo in the middle, which is an Amur falcon. So as you can see from these pictures as well, most species of falcons, not all of them, but many, also have these distinctive dark malar, or also called moustachial stripes, which is a pair of dark facial stripes that extend below the eye. So this has prompted the question as to why so many falcon species show this distinctive trait and why it's not seen in other raptors, and therefore prompted many hypotheses as to what function these malar stripes could possibly serve. So a commonly proposed hypothesis for the function of these malar stripes is that they function to reduce solar glare. So glare is defined as non-information containing light that interferes with vision by reducing the ability to see and distinguish objects when in bright conditions. So black or just dark surfaces absorb light due to just the intrinsic properties of dark pigments, And therefore the theory is that dark markings around or under the eyes, like the malar stripes in falcons, might improve the ability of an animal to see in bright conditions by absorbing any excess sunlight that would otherwise be reflected into the eyes and interfere with vision. So if this was the case, we would expect to see larger and darker eye markings in animals that inhabit regions of higher solar radiation. So while this hypothesis hasn't received that much attention in the scientific literature, there have been quite a number of quite promising studies. So in both masked shrikes on the top left and willow flycatchers, bottom left on the left-hand side, painting the facial markings or the beak with white paint has been found to change the bird's behavior to make them forage less often in sunlight and more often in shade, and also reduces their efficiency at hunting in sunlight. Whereas in the New World warblers, that's the bottom on the far left, dark eye markings and dark beaks are also found disproportionately in species that inhabit very bright habitats. So for other species, like the Ross's gull on the top right, in which juveniles have these dark eye patches, and also mammal carnivores like raccoons and cheetahs, it has often been suggested that dark eye markings could serve the solar glare reducing function, but this hasn't actually been tested scientifically, so it remains speculative and fairly controversial. But probably actually the most interesting evidence comes from humans. So sports players, and particularly American football players, often use what is called eye black. So that's either black grease smeared under the eyes, or it's black stickers worn under the eyes, with the theory being that this reduces glare and enables them to see the ball better when they're playing in very bright conditions. And an ophthalmology study actually tested this, and they found that wearing eye black does significantly improve the ability of sports players to see in bright conditions. So clearly there's quite reasonable precedent in the literature for dark markings like falcon malar stripes having an effect in reducing solar glare. So for my honors project, I set out to test the predictions of this hypothesis in peregrine falcons. So to do this, I downloaded over 2,000 photographs taken across the peregrine's geographic range from 2 online citizen science observation databases, the Macaulay Library and iNaturalist. I don't know if anyone here is familiar with these, but these are both online platforms where amateur naturalists and birders can share their photos, videos, audio recordings, or even just point observations of birds, and in the case of iNaturalist, other organisms as well. So for all the photographs, I then visually scored the appearance of the malar stripe for each bird. So I assigned each bird numerical scores from 1 to 10 based on the size or dimensions, so like the length and the width, and then also the prominence or the darkness of the malar stripe. Then since all photographs also had GPS coordinates attached, I used these to obtain climatic data, so solar radiation, but also temperature and rainfall from Google Earth Engine, which uses satellite data. So the question I was interested in asking here was, do trends in peregrine falcons support the predictions of the solar glare hypothesis? So do we see larger and darker malar stripes in peregrines that inhabit regions of higher solar radiation? And is this hypothesis supported over other potential climatic hypotheses like rainfall or temperature? So in keeping with the predictions of the solar glare hypothesis, I found that 4 out of 5 of the malar stripe variables I scored were positively associated with solar radiation, and that, as you can see from these pictures, peregrines had wider, darker malar stripes and also overall darker heads, or a more hooded appearance in regions of higher solar radiation. So the trends in peregrine falcons therefore support the hypothesis that falcon malar stripes function to reduce solar glare. So the questions to ask now are, firstly, do other falcon species also show these same trends? And also, how do differences in species ecology, like perhaps their habitat or their diet or their lifestyle, affect these relationships with solar radiation? So this leads into my master's thesis, in which I extended this analysis to look at all falcon species. So I followed much the same methodology as the honors project, except this time I downloaded nearly 11,000 photographs representing all 39 falcon species. And also, instead of iNaturalist, I used GBIF, which is just an online database that actually collates data from multiple citizen science platforms, including iNaturalist, but also including several non-English language websites. So it has a bit of a broader scope. So as in the Honors project, I also visually scored the malar stripes of all the birds using scores of 1 to 10. And I saw solar radiation data, but not temperature or rainfall this time, from Google Earth Engine again. So the questions I was interested in asking this time were, firstly, do the trends observed for peregrine falcons, so larger and darker malar stripes in regions of higher solar radiation, also hold both within other species and also across all the species as a whole? And then secondly, how are these trends affected by differences in species ecology, such as their habitat or their diet? So namely, is the relationship with solar radiation stronger or weaker for species with a particular lifestyle or ecology, or do we only see it in birds with a particular lifestyle or ecology? And so counter to my expectations, and quite disappointingly, I actually found that the size and darkness of falcon malar stripes were either non-significantly related or negatively related to solar radiation when looked at across all the species. And indeed, falcons seem to have paler malar stripes in regions of higher solar radiation, which is the direct opposite to what is expected under the solar glare hypothesis. And there were also no clear trends within most species. So no other species showed the trend towards consistently larger and darker malar stripes that the peregrine falcon did. Most of them showed no relationship with solar radiation. And these results therefore do not support the hypothesis that falcon malar stripes function to reduce solar glare. So what these results could possibly mean is either if falcon malar stripes really do serve a glare reducing function, that maybe average solar radiation is just a poor measure of the actual light environment or the actual amount of glare experienced by a falcon. Or else, of course, there could mean that malar stripes actually serve a completely different function in falcons that is totally unrelated to glare at all. So, of course, this does prompt the question now that if falcon malar stripes do not function to reduce solar glare, then what function do they serve? So one thing we did find that was quite interesting is that malar stripe size and darkness were related to habitat and diet independently of solar radiation. So falcons living in more forested habitats had larger and darker malar stripes relative to those living in open habitats like deserts or grasslands, and also species that specialized on birds had larger malar stripes than those that are more generalist feeders or eat more terrestrial prey. So one speculative possibility, therefore, is that malar stripes actually function as a form of camouflage or what is called disruptive coloration, in which the dark markings around the eye serve to disguise the eye or break up the outline of the bird's face to make it less visible to prey. And a potential reason that this would be more important in falcons that specialize on birds is that birds have very good eyesight and are very visual creatures in general. So it's probably more important for falcons to disguise their eyes or faces when they're hunting bird prey than when they're hunting less visual prey, such as insects, rodents, or lizards. And many other bird species actually also have these kinds of disruptive facial masks or facial eye lines, which are thought to make the bird's face or eye less visible to other birds, albeit in the case of this European nuthatch or the ringed plovers, it's thought to instead function to make them less visible to bird predators instead of bird prey. But then ultimately, of course, it is possible that falcon malar stripes serve a completely unrelated function that is outside the scope of this research. So, for example, they could serve as warning coloration to intimidate potential predators or rivals, or they could play a role in visual communication or social signaling, for example, in mate recognition. So another question to ask is why peregrine falcons showed such a reliable trend towards larger and darker malar stripes in regions of higher solar radiation when this trend is absent in all the other falcon species. So the peregrine falcon is actually a fairly unique species for two reasons. So firstly, it has the widest geographic distribution of any bird species and occurs and breeds on all continents except Antarctica, or New Zealand. So the fact that we found a trend for peregrine falcons and not for any other species may even just be a result of most falcon species just not having large enough geographic ranges or occurring in diverse enough regions to be able to detect a geographic trend, and the peregrine falcon being unique in this regard. But secondly, while the peregrine falcon is far from the only bird-eating falcon, or even the only falcon that hunts by fast, agile chasing of birds through the air, it is notable for being the fastest flying of all birds, and indeed is one of the fastest of all animal species. Peregrine falcons reach speeds of around 100 kilometers per hour just in normal flight, and can reach over 300 or even nearly 400 kilometers per hour when diving or stooping in pursuit of prey. So it may thus be that peregrine falcons are unique in having to pinpoint and keep track of moving targets while they're moving at these very, very high speeds. So meaning that they have to maintain very high visual accuracy and visual performance, even in very bright conditions. And so therefore, Malar stripes could serve the role of reducing solar glare in peregrine falcons, despite not serving this role or not being as important for solar glare reduction in other species. So in conclusion, the solar glare hypothesis for the function of falcon Malar stripes was supported in the peregrine falcon, but is not supported in other species. So from these results, we can conclude that solar radiation is not a primary driver of Malar stripe evolution, at least in species other than the peregrine falcon, and that Malar stripes likely originally evolved to serve a different function. So future research can expand on this both by performing functional experiments, for example, manipulating or painting over the Malar stripe area of captive falcons, for example, painting over the Malar stripe with white paint, to see if this affects the falcon's ability to hunt or perform tasks in bright conditions, and also by performing evolutionary analysis to try and determine when in falcon evolutionary history or where in the falcon family tree Malar stripes originally evolved, and also the most likely environment and lifestyle experienced by this hypothetical common ancestor of falcons. So both of these would likely go some way to unraveling the mystery of the function of falcon Malar stripes. So thank you. And I think we have time for questions.
We do indeed. If you wish to ask a question, you can just unmute yourself.
Yeah.
May I ask a question? This is Heather Howe.
I'm just trying to bring up the chat again.
What are you trying to bring up, Michelle?
I can't seem to access the chat right now.
Look at the top of your screen.
Oh, there we go. Yes, there we go. Okay, I can see the chat now.
Okay, Heather, you want to ask a question?
If you look
Should
at
I turn my...
Can you hear me?
Yes.
Okay. If you look at the size of the eyes of the peregrine, it has much larger eyes in proportion to its body size than other birds of prey, or am I just being stupid?
Oh no, I think falcons in general have fairly large eyes. And yeah, actually a lot of the sort of pop culture understanding of raptor vision isn't correct. But the studies, yeah, there have been actually fairly few studies looking at the visual acuity and the resolution of vision in raptors. But what we do have so far, I don't think there's any data for peregrines particularly, but I think it was the American kestrel, which is another falcon species, has the highest contrast sensitivity. So that's the highest ability to distinguish or resolve objects from each other of any bird species. So these things definitely do suggest that vision is very important for falcons particularly.
I was sort of thinking that if it's got very big eyes, it takes in a lot of glare, and therefore it has to have a device to absorb extra light or reflection.
yeah, that could definitely be. Well, you know, that is a lot of the theory behind it. But of course, we didn't find this relationship for the rest of the falcons. Whereas, if anything, I would think that the small falcons and the kestrels even have bigger eyes in proportion to their heads than peregrines do.
I'd like to thank you while I'm online for a wonderful talk. Thank you.
Thank you. So I turn my video off. I don't know if that's... I'm still here.
There's in the chat box, there's a message from Deanie Goodwin saying, fantastic research, Michelle.
Yes, thank you. I'll type a message here as well.
It doesn't look as though anyone else has got a question. So thank you. I really enjoyed hearing about all that. And I'm going to hand over to Johan to do the thanks, the official thanks. Johan?
Hi, everyone again. Michelle, I've had the pleasure of working with you with the education program, and, you know, had a sense of some of that deep expert knowledge you have. But you have a gift that many experts don't have, and that's the ability to make the complicated simple. So your presentation was crystal clear. It held the attention, very interesting, and thank you for such a superb presentation.